But here we can talk about polyatomic ions and how we're going to put them together. Generally, the same thing is going to be hold true. But one additional thing we have to undertake is that, of course, if they're polyatomic ions, that means they have a different number of electrons or than protons. So, if, especially for anions, polyatomic ions, such as we'll do NO3 minus nitrate polyatomic ion, these polyatomic ions, what that means is that this negative charge indicates that it has one more electron than a NO3 molecule would have, so you have to account for that in your Lewis structure. So usually what the game plan is to total your number of valence electrons, and you can do this for molecules as well, but we know that nitrogen has 5 valence electrons, oxygen has 6, and there's of course 3 oxygen atoms in this polyatomic ion, so 3 times 6 would be 18, plus the 1 additional electron for the charge. So 18, 5, and 1 is 24. This polyatomic ion has 24 electrons that we need to account for in the structure. Okay? As you'll see, most polyatomic ions are oxyanions, meaning there's several oxygen atoms bound to a central atom. Okay, so one of the best ways to start about polyatomic ions is putting that non-oxygen element as your central atom. Okay, and then bond the oxygen atoms with at least one single bond to the central atom. Then the next thing you're going to do is just account for the additional electrons and trying to get the octet rule filled up for each atom. Okay, so far we've used 3 bonds, and so that corresponds to 6 electrons, so we have 18 electrons left. So if we put a lone pair around the nitrogen, so that'll be 2, so it'll be 2, 4, 6, 8. So far we've used 8, 10, 12, 14, 16, 18, 20, 22, 24. So that is all the electrons we have, so that's all we can show. Okay, but if we take a look at this species, it turns out that this is not the most stable form of this ion, because as you can see that this oxygen atom does not have the octet rule. What could happen, instead of applying this lone pair here, we could form a double bond here and draw a molecule that looks like this. And you can do the counting and see that each atom has the octet rule if I place all the electrons on it. And so this is the most stable form of the polyatomic ion, and usually you put this in brackets with a -1 charge to indicate that it is a polyatomic ion with an overall charge of -1. Okay, one more thing we have to talk about when drawing structures, and as it turns out, the only real way, absolute way to determine the formula, or excuse me, the structure of a molecule is to go in the lab and do it. Do some experimental technique, usually involving spectroscopy of some sort, the interaction of the molecules with light, or magnetic field. In the case of NMR, will give you information about its structure. These are only, using Lewis structure theory is of course only a prediction. Certainly not always the correct answer, but it is a very, very simple and effective tool nonetheless. One other thing that we'll have to take into account, in addition to trying to get to the octet rule, is achieving the lowest formal charge for a molecule or polyatomic ion. And what a formal charge is the number of valence electrons associated with each atom minus 1/2 the bonding electrons minus the non-bonding electrons. Okay, and so if we do that, we'll actually be able to distinguish between the sulfate polyatomic ion. If we draw the sulfate polyatomic ion and we draw the Lewis structure and we try to get the octet rule for all of, so the sulfate ion of course is SO4 2 minus. If we draw its structure corresponding to the octet rule, we will get something that looks like this. And it turns out that if we take a look at each of the elements, they look like they have the octet rule, and indeed they do, written like this, but it turns out that this is not the most stable structure, and this is not what sulfate looks like in reality. It actually looks like this. A scenario where sulfur actually has more than 8 valence electrons, or what we refer to as a expanded octet. Now, how would we know if this expanded octet is more stable than this one that achieves this octet rule? And that, of course, is by calculating the formal charge. If you calculate the formal charge for each of these elements, the most stable prediction will be the species with the lowest formal charge. Okay, so let's calculate the formal charge on this oxygen. Each oxygen atom has 6 valence electrons. We're going to subtract 1/2 the bonding electrons. We can see that it has 2 bonding electrons, so 1/2 times 2 is 1. And then minus its non-bonding electrons, and it has 2, 4, 6 bonding electrons, or non-bonding electrons, excuse me. So that, of course, equals -1. All of these oxygen atoms have a -1 formal charge. Okay? If we do that for sulfur, sulfur also has 6 valence electrons. It has 8 bonded electrons, times 1/2 is 4, and then -0 for its non-bonding electrons gives us a +2 formal charge. You'll notice that the sum of the formal charges equals the overall charge, and that's be very important to sort of double check your answer. But let's go to the expanded octet version of sulfate polyatomic ion and calculate the formal charge over here. Well, we know that the oxygen atoms with 6 valence electrons that aren't bonded and 1 and 2 that are will give these oxygen atoms a -1 formal charge. We already did that calculation. These oxygens will have a different formal charge because they're bonded in a different manner. Okay? They still have 6 valence electrons. This time they have 4 bonded electrons, 2 in each of those single bonds, and 4 in the double bond. So 4 times 1/2 is 2. And then they have 4 non-bonding electrons, and that gives us a formal charge of 0. Same for the oxygen up here. And this sulfur, which is bonded in a different manner, has a formal charge of 6 minus 1/2 the bonded electrons. It has 12 bonding electrons, so 6 times 1/2 is 6, minus 0 non-bonding electrons, of course, gives us 0 as well. So 3 of the atoms in this configuration of sulfate have a 0 formal charge. And the lower the formal charge is, the more stable we can think that configuration is. The sum of the formal charges still equal our overall charge of -2, and so by calculating the formal charge we can give us a scenario why this expanded octet form of sulfate is more stable than the previous